Back in 2013, when I was a grad student at IIIT Bangalore, I didn't know about PyCon at all, and I actually didn't know about open source at all. So by coming here, there were a few of my friends said there is a conference called PyCon, and I said, why there is a conference for a language? Is it really required? So when I came here and I saw that how a community drives the language and for betterment of all the language, then I got to know that, yeah, uh, this is something even I wanted to do, and I got involved with few of open source projects, and it was a great learning experience. So I just want to give a round of applause to all those developers out there, and awesome conference like this. So yeah, thank you. So before I start the talk, I want to give a brief introduction about what this talk is about and what this talk is not about. Because in natural language processing, it's actually a very heavy research topic, and there is lots of new research coming along every day. So all the things which I'll be talking about, natural language processing, are the things which were in research papers just either 1 year back or this year. So things are pretty fresh and pretty new, and people are still experimenting with it. Nothing has been went into production till now. So, and since it involves, there is a club between machine learning, deep learning, and natural language processing, which is the current research status. So I won't go into mathematical details. The talk will actually motivate you to start working on it, start exploring these things, and do some cool stuff around it. So I'll start, let me just have an idea of the crowd. How many people are actually working with natural language processing? Machine learning? Deep learning? Very few. Okay, cool. So I'll be going through basics, and if you have any problem, we'll be taking questions at the end. And if you want to do math, I'll be outside, we'll sit and do math. Okay, so I'll start with what is actually natural language processing and how does it start it. So so language was always there with us. Why is not? Okay, so language was always there with us. As soon as we got computers, we wanted to understand language programmatically. Why? It's a very obvious answer, because computer needs an interface, and what is the best interface rather than our own language, right? So moving forward, we built something which was there, that how can we understand language programmatically so that we can do automation and we can have computers do stuff around natural language. So these were the things which people were doing, and which is there right now. So what we can do with natural language, since our grammar has a rule, so we can actually follow those rules and say we can compute part of speech tags for each word. So I'm taking English language as the basic, and all these talk will be focused on that, and there will be different rules and different set of things around different languages, say German or Sanskrit, which are heavily grammar oriented. So we know our part of speech. We also know our vocabulary. Our vocabulary is growing every day, but it's still, we can store all of that. And n-gram is a thing which we can apply on any language. N-gram can be a bigram, trigram, or more than that. So it won't consider a word as a word. Every word will be broken into, if it's a bigram, then two character words will be bigrams across the sentences. And word style is capitalization or non-caps, all caps, these kind of things, and noun detection. And this is a complicated problem, but still we can detect nouns. So these are the things we were doing to identify that how we can do something around natural language. So given a sentence, can you process that sentence, and how can you process that sentence so that you can get some information out of it? And if I'm talking about information, what computers can do, they can chunk numbers. So every information which is there, which is called unstructured data, which is text, image, video. So as this talk is focused on text, what you can do with text and how can you convert it to numbers so that you can process it, right? So let's go a sentence. If there is a sentence, let's go word by word. So currently, what is state of the art 2 years ago was researchers was actually doing this. They were calculating. So if you go word by word, you have current word, you have previous word, next word, current word n-gram, previous word n-grams, and pause text, surrounding pause text, word shapes, surrounding word shape, and anything around it. So there are lots of things you can do with it, and you can actually convert everything into numbers. So by numbers, I mean indexes. So a current word is an index in your vocabulary. Similarly, your next word, even a pause tag, you can create an index. So it's all getting into that, and this all will generate some information, and that information is used to understand that sentence. So if a sentence has 10 words, for each word we'll calculate this much information, create a feature out of it, and do something. So if I say feature, let's say there is a sentence and it has all these features. So we calculated all these features and they are in numbers. So what we can do with that? If I go forward with a machine learning model, so let's say I just want to know what is the sentiment of that sentence. So for that, I need to tag few sentences before so that we can learn, right? So suppose sentence 1 will calculate that this is the vector. If I have n features, so it will be n-dimensional vector, and that n-dimensional vector has a tag, okay? And we have some weights associated with each feature. So every feature has some importance to identify the tag. So as soon as we got exposed to more and more training data, these weights will be adjusted. And this weight will be actually the weight of hyperplane separating all those, separating these two classes. So with each training set, that hyperplane will adjust and try to fit the model so that the negative ones will be at one side of the hyperplane and positive ones will be at the other side of the hyperplane. As soon as you finish training your model, once you get the sentence, a new sentence, you again calculate the features, just plug in those weights, and your hyperplane will tell you that it falls into positive category or a negative category. So it's a very simplistic way of explaining a machine learning algorithm, how it works, and how it will work on unstructured data. So what are your thoughts on that? What we are actually doing is, through natural language processing and our set of rules, with lots of processing, we calculate data features, and through machine learning, we just optimize that weight. We just learn that hyperplane, right? So these two fields, if they combine, you can understand your data better. But there is a problem. Is it scalable? It's not at all scalable. There will be new languages, and our language vocabulary will increase. And we are talking about AI here. Machine learning is one of the field which is right now leading in AI. It's one school of thought. So what is wrong with that? The wrong thing is we are doing lots of processing, and that processes are actually dumb processes. So if you are calculating part of speech tag for a sentence, it's a process, it's a standard program which run and which will fail if you have any non-standard thing. Similarly, other features, suppose I'm calculating 50 features, and if you assume every feature is a process, we have 50 processes running, generating some data, feeding it to an optimization algorithm which will run your hyperplane. So it's not at all scalable, plus it's not iterative. As soon as you have new data, you have to again do the same thing. So something is wrong with that, and researchers also find out that, yeah, something is going wrong, and we are not scaling up in NLP. So whatever the research was there for last 10 years was actually superseded by last 2 years research, which was introduction of deep learning into natural language processing. So we hit the basic first. How do we represent a word? So when I said we'll process a word, and if we process a sentence, and I say we will process it word by word. So there is an inline problem with that. our word representation are actually very weak. So how do we represent a word? Suppose I say we'll build indexes. So if we have a vocabulary, and if there is a word which is called nice, and it comes as a 30th index, so we'll create a one hot vector. So this vector is called one hot. It's 0, 0, 0, and 1 at the place where its index is. So 30th index is 1, rest are all are 0. So dimension of the vector is your size of the vocabulary. So this is how you represent, suppose a word is nice, which is at 30th place, and word is good, which is at 45th place. So with this representation, can we say these two are actually same? We cannot. So the main problem is, how do we represent the word? Our word representation does not convey any information about that word. We calculate information about the word by the surrounding neighborhood words. So if we improve our representation of word, we'll be saving a lot of computation, and we'll be doing some more analysis on top of that. So there was an answer for that earlier, and people actually thought about it, and they created word nets. So word nets are a tree or a graph, you can say, and they actually capture the hierarchical information about all these words. So if you have awesome, good, nice, okay, it's a hierarchy, and they are connected, and their distance tells you that how good they are connected, and there are nouns also. But there is a problem with word nets too. It's a lot of manual labor by linguists. So they create it over the period of time, and Princeton has highest word net right now. You can access it, and I'll be showing Python how we can do it with Python. So word nets has problem for, it's actually a lot of manual labor, scalability issues will be again there, and as soon as you have new words, how do you associate those new words to previous words? Again, you have to do a lot of computation, and there will be a lot of validation from linguists, and they may not agree. So if LOL, LOL has to come into WordNet, so how do you connect it? And few people will not even agree that it's not even a word. So there are lots of things has to go into that, which is language specific. And the biggest problem is nouns. We are generating nouns every day. So how do you incorporate all the nouns in that? And how do you say that this noun is actually similar to that noun? So all these problems are there. I'll just give you a demo of word nets through Python. NLTK is natural language processing library in Python. Through NLTK, you can see that they have these word nets saved into that in corpus, and you can access those word nets. Okay, so this is how we can access word nets. And WordNets has lots of information and lots of rules in that. So you can define is a relationship, which is called hypernyms. So if I say, so this demo shows that panda, and okay, so let's say, so that is not rendered. So let's say we want to say that how many synonyms are there for nice, and it will show you the hierarchy of all those synonyms. Similarly for these nouns also. And it also tells you that what is the region and domain. So there are lots of information in word nets you can get out of it. So what is the etymology of a word, and how it is connected to which region it is connected to. So Pakka is an Hindi word, so its region is India. So these kinds of information you can take from word nets. What I can do is I'll switch to these demos at the end, so that it will be straightforward. Again, let's get back to where we were. So word nets, we say that we have some problems with word net. So let's think about how do we associate with the word, right? If I say a word, there are lots of things in our human mind which goes inside it. So we associate it, if it's a noun, we associate it with a person, and we create a context around it, right? And that context could be taste, smell, time, visual, or feelings. So there are lots of hooks with a word which gives us that, okay, this word represents this. So what we can do programmatically. So there is a code which says that you are an average human of the 5 humans around you. And there was similar quote in natural language processing which says that you shall know a word by the company it keeps. So that is for there to create context. So how easy it is to create context? We can actually create co-occurrences matrices, and it's one of the most successful ideas of NLP. So how do we calculate co-occurrence matrices is this way. So suppose we have a corpus, and that corpus represent these three sentences, which is I like deep learning, I like NLP, and I enjoy flying. So in that, if we create a matrix which has every single word from that, so the dimension of the matrix is again n cross n if you have n words. And we are creating this co-occurrence matrix as one neighbor co-occurrence matrix. That means every word which is just adjacent to another word will give a count 1. So, and increase the count 1. So you can do that for higher context also. So if that matrix is there, and so we represent our complete corpus in that matrix. Again, there is a problem with that. Yes, we can do some analysis on that matrix. Again, we have converted our corpus into a matrix, numbers, but and we have represented all our text data into numbers, which actually capture the context of the word. Again, it is very high dimensional. If you have millions of words, again it will be a million cross million matrix, and you won't be able to do much processing on that. And if we run, and this matrix will be actually sparse. So by sparse, I mean there will be lots of zeros, because not every word is associated with every word, and they don't come together. So with lots of zeros, if we run a classification algorithm, there will be a problem. I'll show a demo of co-occurrence matrix, but at the last, because I have to again switch back these things. So what we can do with co-occurrence matrices is we can reduce the dimension of a matrix always, right? So if we reduce the dimension, the matrix will be smaller, and it's always if you have a high dimensional data which shows the dimension which we understand, and if we reduce the dimension, there will be some latent information there. So a dimension can be a dimension of similarity. So it's quite abstract, and we cannot understand which dimension it is, but we can reduce the dimension using SVD. So SVD is singular value decomposition. How many people know here SVD? Okay, great. I won't go into math of that. So SVD is a method by which you can actually reduce your matrix into a smaller matrix, and it will be having low dimension, and those dimensions will be representing the most important features of that matrix. So any matrix you can actually represent it into these three matrices, and you can reduce the dimension. I won't go into math, and this demo I'll show you later how we can calculate SVD through Python, and how we can represent the word in low dimension space. So again, we have another problem with SVD. So the problem with SVD is calculating the SVD on that high dimensional vector, high dimensional matrix. And if you have, again, billion words, converting into million words will again not solve problems, right? So billion by billion matrix, if you convert it to million by million matrix, it's still million by million matrix, and you can't do away with that. So again, inherent problem with SVD is calculations and iterativeness. Again, if I have a new sentence in my corpus, I have to calculate the SVD of the whole corpus again, and then do this stuff. So this is where last 2-year research has contributed. This is the algorithm called Word2Vec. It's by Google, and by Thomas Mikolov and Jeff Pennington. And there is another research happened in Stanford by Richard Socher and Yosha Bengio, which are very famous guys in NLP. So what they have done is, instead of we calculating the lower dimension matrix, why don't we learn the lower dimension matrix as it is? We don't go into high dimensional matrix at all, and we learn the low dimension matrices directly. So they calculated, they devised this algorithm called Word2Vec, or GloVe vectors, global vector of words. It's actually very fast, and you can do a lot of things with that. So what do we do in word vectors is, we said, right, we can understand a word by the company it keeps. So Instead of going to the singular value decomposition and calculating the co-occurrence matrix, why don't we just predict the our context? So there are two school of thoughts in Word2Vec again, say two algorithms, which is one is called skip-gram model. So what this skip-gram model does is, suppose you take a sentence and you just say that I'll look at this sentence with the context of 5. So if I have a center word, I look into 3 words on the left and 3 words on the right. And if I have a word and if I start predicting the words in my context, so that as much more I'll see those words together with that sentence, together with that center word, will be having its probability increasing. So what we do is we maximize the log probability of the context of the word. So I'll represent it in pretty simple manner. Suppose this is the sentence, and so sentence is very long. Say it has lots of words, W1 to W12 or W100, but I'm only interested in a context window of 3. So I'll take this word WC, and what I'll do is I'll run a log. I'll run an optimization algorithm which will increase the probability of these. Which will increase the probability of these context words. It's all going highly mathematical, and it's actually very difficult to give a demo on how we'll be calculating it. But I'll be uploading all the IPython notebooks which can actually do all this stuff, and I'll show you a demo also. But that will not be too much informative in this talk. But I'll be outside and I can go through all those things. So what's good in Word2Vec is, first of all, it is unsupervised. We don't have to tag our data. It's just dumb text. You just give it to that. It will go word by word and predict the probabilities of which are the words which come with that. And what happens with Word2Vec is they actually create a low-dimensional space. So that lower dimension space it depends on you how much dimension you want. You want 1,000 dimension or 300 dimension. So that will be our vector, instead of a complete one-hot vector, which is the size of the vocabulary. So these lower dimensions space can be anything. It can be a space of, say, a dimension of similarity. This dimension only shows the similarity between words. Or it can be a dimension of sentiment. This dimension shows that these words are actually aligned with their sentiments. Or they can be all caps dimension. So in that dimension, every single word will be capital. Or it can be anything. So it's up to you to figure out and explore what other lower dimension space are actually talking about, and they are abstract and very hard to find out. So it was there that Word2Vec actually captures the dimension of similarity, right? So dimension of similarity is pretty broad. So it can be similar in anything, and all these algorithms, they capture syntactical information as well as semantical information. So if I say syntactical information, singular or plural. So after that, after all these algorithms, we calculate a vector, right? For every word, we have a vector which is lower dimension vector, say 300 or 1,000 dimension vector. So in Word2Vec, you can get a vector out of every word. So we said that our representation was wrong, and we were not, our vector representation of every word was not carrying any information. But after that, our vector representation of every word has a lot of information. So if I subtract that vector of apple minus vector of apples, it is exactly similar to vector of car minus vector of cars. And it's actually similar to family minus families. So that means so if I subtract one vector from another vector, it will be a dimension. Again, it will be a vector, right? And if we go into same dimension, that dimension is actually capturing a singular plural relationship. So, and there are lots of interesting things you can do with that. Vector of shirt minus vector of clothing is equals to vector of chair minus furniture. So shirt is a type of clothing, and chair is a type of furniture. Similarly, this is very famous example. Sorry, there is a typo. So vector of king minus vector of men is actually equal to vector of queen minus vector of woman. So it is actually calculating here that all the semantical information which is not anyway in syntactical information. So how do we calculate this dimension of similarity? So here the topic of this talk is solving logical puzzles through natural language processing, right? So the logical puzzles which you can solve are analogies and odd man outs through that. So how do we solve analogies? So suppose and how do we solve analogies through our brain? If we have not seen that word, we cannot solve its analogy problem. And if we have not seen that word, we cannot solve its odd man out problem. So it's actually, this limitation applies to that algorithm as well, which we human has. And so if man is woman, and what is analogical to, if man and woman, and then what is analogical to king and what, right? So that will, so answer is queen. So in word2vec, you can just simply say add king minus men plus women minus, so that will be queen. So if you can see that man and woman direction is exactly similar to king and queen direction. So if we have these three information, we can directly jump into queen. So in this way, you can solve your analogy problems. And in this way, you can also solve your odd man out problem. So how do you solve odd man out problem is, suppose when we were training our word2vec model, when we are calculating all these probabilities that which word comes together, what we can do is we can just infuse some bad data, a random text, not even random, which is wrong in grammar, right? So that is called negative sampling. So we are giving wrong data to the algorithm, and we'll say that this is wrong. So we just tag that this is, say, all the nice words are 1, which is grammatically correct. All the wrong words are 0, tag to 0, which are grammatically not correct. So algorithm will learn that these words should not come together, which are not the part of the grammatical structure. So if we go into odd man out, it will say that these words have not come together in any dimension. So this word is actually out of that. So I'll go through all these demos now, so that we can see that in action. So I was talking about SVD. Is the font clear? Okay. So these are three words: I like deep learning, I like NLP, and I enjoy flying, right? So using NumPy, linear algebra library, we can directly calculate SVD, and these are our words, right? I like NLP, deep learning, and all these words are there in this thing. And if I create this context matrix manually, you can always create it programmatically. And if you calculate SVD of it, so this this matrix, which is a context matrix X, is actually is now breaked into three matrices: U, S, and V dash. And so U has all these eigenvectors. So if we show these eigenvectors on this two-dimensional plane, we can see that these are now coming in some patterns. So this is very small, and it will actually not capture any pattern. If you do this with large data, it will capture a lot of patterns. So those kinds of patterns you can see here. So these are TSNE visualization, which is used for visualizing high-dimensional data. So you can see that parliament and elections are coming together, and banks and reporters are actually ministry and union. So all these things. So this is how we'll calculate SVD and move forward. But I'll go into demo for word2vec. So Python has an awesome library called GenSim, and you guys can go through that. It's very simple. And Radim Rurik is the author of that. So word2vec is actually written in C. So he has converted into Python, and it's actually very fast. And you can do distributed programming also, because word2vec is limited to high volume data. So Google has given a trained model of word2vec, which is 100 billion word model. It has 300 million unique words, and it contains almost everything we speak today, even Indian words. So you can check your name there, whose name you are similar to. So this is how. So you just load that model, and that model is there in binary form. And if you load that model and you say that you give positive as woman and king and negative as man, so you'll get that queen as the highest number. So this is how you'll solve your analogies problems. And so this is your, so it has another method called doesn't match, which is odd man out. So if I say breakfast, cereal, dinner, and lunch, so which of these does not fall into same category is cereal. And you have similarity is there, and it's a dictionary. So if you want to see that what is the raw vector of this computer, so this is the vector. This is 300 dimension vector. So once you have vector, you can do all the stuff you want to do with your machine learning libraries. So you can learn sentiments, you can do name entity recognitions and all. And it is completely semantical. So sushi and shop and Japanese and restaurant are actually similar. And yeah, this I just cooked up. So because we were talking about Modi and Kejriwal a lot. So if I say which is most similar to Modi, so these are the results Word2Vec give. So it depends on your data. So this data is actually last 10-year Google News data set, and they trained upon it, and it's a very huge model. It takes around 4 or 5 GB of RAM in your computer. Okay. I'll quickly go through one of the things which is about Word2Vec is, or maybe I should just, okay, so if you want to train your model, so you have to create your you have to create your text to sentences, and then you can train your own model and then do queries on this. So I have other things which I can talk offline, and I'm open for questions right now, if you have any.
Hi, this is more of an announcement rather than a question. My name is Amit Rao, and I'm a freelance technology consultant with a background in research and development in natural language processing. So I've created an open space slot at 12:30 for people who are interested in natural language processing and Python. So as Ismail said, there is a NLTK toolkit, and I think there's an opportunity to create a community of people who are interested in NL processing. So those of you who are interested, please come to the first floor at 12:30, and we'll brainstorm on how we can contribute to this. Thanks.
Sure, thank you.
Hello.
Yeah.
Thank you for the great talk. I have two questions.
Okay.
The first question is, when we are talking about Word2Vec, you said it is based on context-aware predictions,
okay,
which is maximizing the likelihood of a word nearby.
Right.
So the idea that was responsible for the Word2Vec was that the original co-occurrences model was very huge to store, right?
Right.
It was n-square implementation.
Correct.
So can you tell me how exactly they are storing the context out of a word in Word2Vec?
So Word2Vec is a neural network. Yeah. So the algorithm is neural network. So initially you give one hot encoding as your first layer. Second layer is your dimension. Suppose you want 300 dimension vector, you train it to just 300 dimensions. And after that, you just output that word again. So once you are calculating gradient descent, and that time you'll calculate gradient descent or any optimization on the weights of maximum likelihood of your context words.
So aren't we, sorry.
So you'll save that as NumPy arrays.
Okay, so aren't we actually constraining the model to understand the limit of context out of a word? So there is a possibility a word is associated with another word which we are not allowing it to train on because we are putting a constraint of dimension.
So that depends on your computational power. Okay, so your context is free. You can take 100 left and 100 right word context, and you can increase your dimension to say 2000 or 5000. So that is tuneable. That is a parameter which is in there in algorithm.
And one last thing.
Yeah.
When you were talking about the vectors in n-square co-occurrences, so you gave an example of, say, the word is nice and it is at the 30th index, so there will be a 1 on that point. So that will generate an n-square matrix, right?
Right.
So right now I was thinking, if we take a straight off single vector where words are indexed with their index number only. So
Correct.
nice is a vector that is connected directly to a position 30
Correct.
in a linear index, right? And to associate a word, we can add it index. We can add the indexed weight. Suppose there are 100 words. and this thing is at 30, so its index to it is 0.3. And we want to associate it like nice weather. Weather is at 70th index, so it is 0.7. So we can add 30 and 0.7. So 30.7, the number itself is some way signifying that nice weather is a context.
Correct.
So, I mean, I don't know, I just came up with it, but
Right.
that is a very nice way of linearizing a n square order problem.
Correct. That is the way, and people are actually doing it. But it's very limited to your context. If you train a model, that is only limited to your own context. It's not a generalized like word-to-vec that you can do a lot of things. So in your view, nice and weather, you are giving the weights. You're not learning the weights automatically out of the corpora, right? It's your view, so I can always disagree with your view that don't associate nice with weather. I associate awesome with the weather, and I give 0.7. So there are these kinds of problems are there.
Okay. One more question out here. Up here on your right. Yeah.
Okay. Yeah.
Hello.
Yeah.
So one of the things you talked about right now using these vectors, right? So you're associating some words in its neighborhood, and you're predicting a likelihood that the similar words will appear next to it.
Correct.
Right. So how do you handle multiple meanings, right? Like nice, right? Nice could have 3 or 4 meanings. It could be nice as in nice. It could be something talking about a nice level where it does not mean good, like the CPU nice level. Or you could be talking about the nice biscuit,
Correct.
right? So when you create these vectors, how do you account for multiple meanings of words, which is fairly common? Apple is also a very common
Correct.
example.
Yeah.
A, that, and B, computational performance versus its like accuracy, right? Versus say a posting list and the WordNet with links on the graph.
Right.
What would its trade-off be?
So these problems are there. So a disambiguation of the word. So this problem is there, but what you can do is once you have these word vectors which actually have some information about that word, you can again train them. So word vector is not a trained model. It's actually words. So whatever the words you are saving in your vocabulary as one-hot encoding or in WordNets, you can have word-to-vec and then again train your disambiguation algorithms.
Sorry to interrupt. Actually, we're like really short in time. You can take these questions
Yeah, sure.
afterwards. Okay. So just don't be mad at me because we're really short in time. Okay. So thank you for such a nice talk. Can we have a round of applause?
Thank you guys.